Welcome back. Let's do a mutual inductance with mesh current. So here is our circuit. It's one of these guys going around connected to one of these guys. And then you've got another inductor in close proximity. So these are close enough to where the magnetic fields are going to affect each other, and there's going to be some mutual inductance M. And this is an inductor with an inductance L1 and another inductor with an inductance L2. So L1 and L2 are the henries, the self-inductance, actually, measured in henries. And then M is the mutual inductance. And then R0, and let's see what's given. A bunch of stuff is given here. A whole bunch of stuff is given. The L values are given, which I could write on here, but didn't for some reason. So 4 henries, and L2 is 16 henries. And the mutual inductance has been calculated for you. That's 2 henries. And then the resistor, R0, the load value, I suppose you could think of it as a load value, is 32 ohms. And there's a bunch more stuff given too. Also given is, well, they give you these IG. So this is the source. This is the source I sub G. So it has a, we're going to use mesh current. So this will be the mesh current IG. And then there's another mesh current here called I2. And those are actually given. So I sub G is a function of time. It's given as 8 minus 8 e to the minus t amps. And I sub 2 is given as e to the minus t minus e to the minus 2t amps. So it's good to plot these things. So this first guy looks like it starts out at 8. Or actually it starts out at 0. It starts out at 0 and goes up to 8. So it's asymptotic to 8. This is I sub G, it's a function of time. And I sub 2 has some guy going up and another guy going down, and the down guy is going to win, and it goes up like that and like that. So it goes up to a local maximum, which I actually solve for, but it doesn't matter. Okay, so this is all given. And we're asked to find V1 of t and solve that at 0. That's what we're asked to find. And where is V1? V1 is the voltage across this power supply, or this current source. It's a current source. It also has a voltage associated with it, which makes it a power supply. So yeah. So before we go on, let's remember that we have two kinds of inductance. We have self-inductance, or V equals Li prime. This is for a single inductor with a current through it. A single inductor with a current through it will induce a voltage in itself. Then we also have mutual, given by V equals Mi prime. And now this is for two different inductors. So a current in one inductor will induce a voltage in the other inductor, and vice versa. Okay, but it's the current in one will induce a voltage in the other. All right? That's self and mutual. So let's write a couple of mesh equations and see what happens. So in mesh current, we're summing the voltages. So what do we have? We have voltage terms, and by Ohm's law we have IR terms, and then we have Li prime, right? That gives a voltage. And then we have Mi prime. So we've got 3 different kinds of voltage terms that we can sum. Okay? And let's write mesh I sub g. So going around this guy here, you're coming into V1 at the negative terminal, so it's going to be minus V1. And then there's a voltage across this inductor. There's a self inductance. So there's a voltage across this inductor here due to Ig. And that's just L Ig prime. This is the self inductance, the inductance of this inductor times the derivative of the current through it. So this is self, and you could label that right here as self. And that's the primary terms, the terms due to Ig. These are due to Ig. Okay, then these two inductors are mutually coupled, so the current in here is going to induce a voltage in here. And I forgot the dots. There's a dot here and there's a dot here, which helps us figure out the signs on this stuff. So we have this equation. The voltage induced in this guy is going to be the mutual inductance times this current derivative. So it's going to be 2I2 prime. This is the mutual inductance. M is the mutual inductance, and I2 is the current in this inductor is going to induce a voltage in this inductor. And what we're doing is we're summing the voltages around this loop. Okay, so we need the self-inductance here, and then we need the mutual inductance from this current inducing a voltage over here in this loop. The only thing tricky here is what the heck is the sign? Well, that's not the only thing that's tricky, but the sign is tricky. Let's think about that for a minute. It's good to draw a little sketch. So what do we got going here? We got I2 going this way, and there's a dot here, and then we've got a dot here, and we wrote a Ig equation going around this way. That was considered our positive direction. Let's say it that way. So here I've got current leaving the dot. That means the positive sign will be away from the dot. Okay, so current I2 leave dot, therefore the positive is away from the dot. The positive sign in the induced voltage will be away from the dot. Okay, this away from the dot means we're coming into a negative sign basically. So this term is negative. Okay, so that's why this thing is negative. Is this. You got to apply the dot convention for voltage, which is what I just did, and don't confuse that with the dot convention for energy, which is a totally different thing. Okay, that's that guy. Turns out that's enough to get our answer. So we could solve this for V1. It's going to be 4Ig prime minus 2I2 prime, and we were given Ig and I2. So all we need to do is take the derivative of these two things and plug it in, and we've got an expression for V of t. So this guy here is 4, and the derivative of I sub g is what? It's just, well, the 8 goes away, and then the minus 8e to the minus et becomes 8e to the minus t, the indestructible e to the t. You can take the derivative forever, and it never goes away. It's indestructible. And then the 2, and then I2 prime, derivative of this thing is minus e to the minus t, and then this one becomes plus e to the minus 2t. with a 2. So 8 times 4 is 32, and you could subtract one of these guys and then multiply times 2, and you get, well, you get minus 4 e to the minus 2t, which isn't obvious, but there's some weird exponent rules going on in there. Whoops. No, it's 34. Because, let's see, you get 32 e to the minus t, and maybe you get another 2 e to the minus t, which makes 34 e to the minus t, and then the 2 times this 2 gives you the minus 4, is a negative sign. And yeah, anyway, this is what you get, 34 e to the minus t minus 4 e to the minus 2. Yeah, they get that thing right there. All right, then it's good to plot these things. I'd like you to plot this stuff whenever you have a function of time, and here's a function of time. So this is v1, so let's see, at 0, this guy is going to be 1, and 1, so it's 34 minus 4 is 30, so it's 30 volts, and then you can't really tell exactly what it's going to do, but I'm going to bet that it's going to go down like this. It's possible, you know, because you have these exponents here and they're not the same. It's possible one of these guys could win, and it's generally speaking, when you have these kinds of things, they could go up a little bit or something. I don't remember if I plotted this in a calculator to see if it has this shape, but you know, that's good enough. I'm just going to put a question mark on the shape here because I'm not really sure that it goes down immediately. It might kind of go up. Anyway, you can look at that if you want. But that's the v1 of t that we're asked to find. And then we're asked to find v1 at 0. So all we need to do is solve this at 0. So it's going to be 34 e to the 0 minus 4 e to the 0. It's 30. That's what I already did. So yeah, there it is. The only other thing that we could do, well, there's a couple of the things that we could do. One of which is we could write the other mesh equation. Just for kicks, let's go ahead and do that, right? So what are we going to do? So we're going around this loop right here. And we've got terms of this type. There's no straight out voltage, but there's a resistance. So there's IR, and then there's the self-inductance voltage term here due to I2. Then there's the mutual inductance voltage term due to IG. So going around the loop, you've got 32 I2. This is just the IR term. This is Ohm's law term. And then you've got the self-inductance, which is going to be 16I1 prime. That's the self-inductance. And the sign on that, here we're doing self-inductance, so the dot doesn't matter. It's the sign on that is, well, I can make a little picture. We have I and we have V, because that's just self-inductance. The voltage is going to be at the current coming in. That's how the self-inductance equation is defined, and that matches our loop direction. So it's like a resistance. It's always going to be positive, really. When you're writing a mesh current equation, it's positive for resistance because the resistance is fighting the current, and likewise it's positive for self-inductance because the self-induced voltage is fighting the current. So those are always positive. But then you have the next term here is this mutual inductance, and that's a little tricky. So it's 2IG prime. That's the mutual inductance. So those are the three terms that sum to 0. And then the sign is the tricky part. Once again, you can draw a little picture here. So we've got this guy has got Ig going through him this way. That's the loop we're writing. No, we're writing the I2 loop. And so here's the this is the I2 loop. It's going that way. And we're leaving the dot here. Actually, yeah, we're writing the oh, this is I2, sorry. We're writing the I2 loop, and we're trying to find the voltage induced by Ig. Okay, so here are the currents entering the dot, which means the positive sign is going to be at the dot, which disagrees with our I2 loop direction, so this is negative. So I could write that out. I could say the current I sub G is entering the dot. Therefore, the plus is at the dot, so that's where to put the plus sign. And then how does that relate to the mesh current equation we're writing? It's opposite that. Opposite the mesh direction, so it's negative. Up here, it was the current was leaving the dot, so the plus is away from the dot, which also happens to be opposite our mesh direction. Okay, that's it. So there's about 6-8 different ways to mess this up. It's inherently confusing. Go slow, and let me just kind of check this over real quick. Yep, I checked it over. Looks good. Okay. So anyway, we wrote mesh Ig, and that was useful for getting V1, which is what we're asked to find. And then we wrote mesh I2, which wasn't useful for anything. It was just for fun. The other thing that you could do that I'm not doing is you could check these equations to see if they make sense, because you're given Ig and I2. You could take the derivatives of those and put those in here and see if they check out. And they would, especially if you didn't have this mistake right here. Sorry about that. So you're given I2 and Ig. You could take the derivatives and you could plug those in here and see if this equation in fact does equal 0. I think the homework asks you to do that. Guess I could put a little more notations on here. This is due to I2. That would have helped me catch this I2 boo-boo. And this is the, it's kind of like superposition, right? Like we were doing with resistors in chapter 4. It's like superposition kind of, except, a little bit different, because the current is, not actually through this device. Only the voltage effect appears in this device. The current is actually in the other device. It's like magic. All right. See ya.